Now, when we're describing things like rain, is classified as precipitation because it's any water falling from the sky, whether it is solid, liquid, or solid or liquid. And so that's one thing that we look about when we talk about something called weather. And I think we don't quite understand exactly what the definition of weather is. And so here is the simple definition. Weather is a collection of data at a certain time. And so the weather is the temperature of the air, the humidity of the air, the pressure of the air, the cloudiness, and what kind of precipitation is given at any time. And so you have weather all throughout the day because you have different conditions all throughout the day itself. Now, most of the time when we say weather, you're probably thinking about climate. Climate is different. Climate is the average type of weather that you have in a certain area. And this is averaged over years. And so, the average weather in Puerto Rico when I lived in the Caribbean was this. Lows were 78, highs were 88, the humidity was 98%, and in the afternoon it rained somewhere on the base every day. Okay, that was most of the time. And then there was August when it got hot. Okay, and so on average it was this is what we found all the time. In your home, the average climate, the kinds of weathers that you would expect, you buy your clothes based upon this. How thick your coats are for the winter. You know, how many clothes, how many shorts you have because how long your summer is. How hot does it get? And so that's what you think about when we describe places with different climates. But weather is a single measurement or a collection of measurements at a single time. Now, to simplify this, we usually take weather reports or measurements of weather at certain times of the day, and they are reported to a national site that collects all this data set. The organization is called NOAA, and it is a site of information that every one of the meteorologists use this data site to predict the weather. What actually happens is there are some of the most complex computers in the world, the fastest computers in the world, are used to do weather predictions because there's so many data variables. It takes the largest computers to do this. The other components that these computers are used for is to do development of nuclear weapons and weather. Those are the two applications that they use for these fastest computer sets. Now, when your weather person decides what he or she is going to report, what really they're doing is they're taking the top 7 or 8 weather models that have been created. And what they'll do is they'll compare all of those 7 weather models. And if 6 of those weather models agree, then they are pretty confident to tell you that the weather is going to be like this in the next couple days. Although that 7th that calculated something different could be completely right, and the other 6 are wrong. And so, but there are different ways to set up how you use the data, and so there are major models that are out there that are calculated to and given out all across the country, and basically everybody uses the same data. It's how they interpret that. Meteorology is actually a study. It's a scientific study, and it involves a lot more math and computer programming to actually do that degree than you might expect. Unfortunately, we have people in the news department that would like, and sometimes you get a weather person who is very, very handsome or very, very beautiful to read the weather, but they're not actually the ones interpreting the data. The person like that is usually in the back, and she or he is probably not as photogenic as the ones they put in front of the camera. Okay? Weather is powered to simply do 2 things. It is to make the Earth the same temperature all across the Earth and to distribute the humidity evenly all across the earth. That is the reason why we have weather. That's the reason why we have all these changes. Now, will we ever make the Earth's temperature exactly the same all over the Earth at any one time? No, you can't. And the simple reason is this. Because we are round and we get energy from the sun, there will always be one face that is being warmed, that are facing the sun, and the other side is cooling because it is away from the sun. And so all the time, one half's getting hotter, one half's getting cooler. So we'll never get it even. But because we have atmosphere, the heat from the hot side tries to roam around to the cool side, and we get wind. Okay? And the hot air carries lots of water. When it gets cool, it falls out, and we get rain. And we have all the weather that we see is because the earth, the atmosphere is trying to distribute it evenly. All right, so weather starts with the sun. So it's the sun that starts it all. And so the sun is shining all sorts of energies at us. Light energies, UV energies, also heat energies. The heat technically is called infrared energy. And so heat and infrared energy are the same thing. And it will warm up the water and the land. And so they get warmed up. And then the water and the land will give off infrared energy and warm up the atmosphere. And so some of the energy gets deflected by the clouds, some energy gets deflected by the ice, and some energy doesn't actually get all the way down to the water or the land, although most of it does. Some of it gets absorbed in the UV range in the ozone layer. So a tiny bit of energy actually warms the atmosphere directly, but most of the energy actually hits the water and the land. And so insolation stands for incoming solar radiation, the types of energies that come from the sun. So insolation. Now, here is the ideas about this. So all of the energy that is coming from the sun is coming down. So 100% comes to us. Okay? Stop. We lose 30% completely by reflecting off the ice and the clouds. So we don't even absorb 30%. Okay? This 19% gets absorbed in the atmosphere, mainly the ozone. Little tiny fraction actually warms up the atmosphere. Most of the energy hits the land and the sea. Okay. All right. Let's say, and there's an example of this. Okay, so it is nice and sunny out there, right? And I've got a parking lot right here, right? And I could take you all out and have you come on this parking lot, stand on the grass, and I ask you to take off all of your shoes and socks. Okay? Then I go all the way down to the end of the parking lot. And I take a dollar bill out and I put it on the ground and I put a rock on top of the dollar bill. All right. It is 2:40 on a July afternoon. I say, anybody who wants to walk all the way down the blacktop of the parking lot can come and get the dollar. How many people would go and get the dollar in your bare feet? Okay, 1, 2, a couple. All right, by doing that, what are you risking? Burning your feet, right? Now, if I put a $20 bill Anybody else? Oh, see. But $100 bill. No, you got to walk. Okay, you got to walk. No, you got to walk. Yeah, how fast do you walk? Okay, but you get what I'm saying, right? That asphalt is hot, right? What made that asphalt hot? What kind of radiation? That is a good answer. The type of radiation that hits it is light. Okay? The light hits the black asphalt because it absorbs all that light. All right. The asphalt has energy in it. Is the asphalt glowing? So it absorbs light, but it doesn't give off light, does it? It absorbs light, and the energy is changed into the area called infrared, which is heat. Okay? And so most of the Earth is warmed by the light energy. It absorbs it, and it gives it off as heat. And that heat is now radiating off of the land and the ocean. Now that heat coming off, which is 51% of all the energy that the sun gave us, 45% of it warms the atmosphere. So directly, the sun warmed the atmosphere only 19%, but 45% of the energy had to hit the land, be converted into heat, and that really the land and the water is making the air hot. 6 of it goes straight up and is lost immediately. Over time, we will lose the rest of the energy leaked out to space. Now, our atmosphere allows light to come through, but the atmosphere traps heat inside. It is just like a greenhouse. You can grow tropical flowers in the middle of winter if you're inside a greenhouse, because the greenhouse has glass that allows the light come down. It hits the soil gets warm, heat comes off, but the glass traps the heat inside. In actuality, in the middle of winter, you actually have to raise the windows to make sure it doesn't get too hot, because that greenhouse effect keeps all of that heat inside. The same way, the gases in our atmosphere will keep the heat inside, and there is a balance point between how much we heat and how much heat goes off. If we don't have enough atmosphere to hold in the heat, we would be colder overall. That's not necessarily good for us because things wouldn't grow so well. But if there is a change in the atmosphere that holds more heat in than what we're used to, then it will leak out slower, and overall, we may be a little bit warmer on average than before. This is the idea behind what was first, and I think incorrectly termed, global warming. Probably more descriptive is climate change, in that if we mess with the balance, things are going to get messed up. And it can get messed up in so many ways. Now, why is it bad to talk about global warming? Well, if it's global warming, then everything should get warmer. And if one example in one place on the earth gets colder, then someone says, it's not global warming, it's not all warming up. Okay. And that's some arguments have been made that way, that not every place on earth is getting warmer on average. Fine, I can't argue that. That's real data. But here is what happens. If you mess up the balance of energy coming in and coming out, you can change the climate, meaning this. Well, in the Midwest, we grow lots of food because there's lots of light and enough rain to grow food, right? But if you change the climate and it just doesn't rain there anymore as often as it once did, then you may not grow as much food. Well, if it doesn't rain as much there, it's going to rain somewhere. And it might make our cities a place where lots of rain comes down, which would be a great place to grow food, but we've got a city there. Okay, we as people, if we can't grow food here and the area where there's land, and this place now would become a place that we could grow food, but we got a city, are we going to move the city over here and plant here? My grandpa owned this land. This is my land. I'm not selling this land. This is my land. Even though we know that it might be good for us to do something, we're stubborn. Stubborn enough to kill ourselves. Right? And so if we are doing things to change how we utilize the land, that could be a bad thing. Okay? And there is a debate about particularly the idea of global warming or climate change. There's a lot of scientific data out there, but there is also a lot of things posted on the internet. And since anything posted on the internet is absolutely true, then there is some people that are that don't believe in what the scientific data is saying. I don't know why that is, particularly. There is resistance to the idea that we might be contributing to the fact that the climate may be changing by how we're interacting with the earth. But I think it boils down to this, is that if we're doing what we're doing and we're making lots of money, don't make me change, because I might not make enough money. In a lot of senses, the status quo makes some people a lot of money. To have that change, some of those people may not make as much money. And so there's a lot of resistance to change. It would be just like, and it kind of correlated to, we are really based upon a petroleum standard for energy, oil. Okay? Not to say that's good nor bad, not to say that's going to ruin our climate or not, but here's the deal with that resource. It is finite. It will run out. Right now, we're not running out. But at some point in time, we will run out. You can't avoid that. If we base everything upon that and we run out and we have no alternative, this generation ain't going to suffer, but someone will down the line, because we aren't looking forward to providing opportunities for other generations, because we're a little bit greedy right now. And it doesn't have to be everybody greedy, but if we don't do anything about it, we may be contributing to those that are, because it's a little bit too hard to do. Okay, or it might cost us a little bit more. And so nobody wants it to cost any more. But these are problems that we have to consider. Okay, so the sun is heating the earth. Got that? And one side gets hot, one side gets cold. It gets more complicated than that. Just because the sun is shining on that side of the earth doesn't necessarily mean that it's all heated evenly. Okay? And it is because we are a sphere and the earth is curved, that affects things. So, an example, if I take a flashlight and I shine it directly down on a desktop, get a nice tight beam and it's really bright, right? Okay? But if I take that flashlight and I put it over to the side, then the light coming out doesn't change, right? But that beam gets smushed all across the table. Does that light that hits the table look as bright? Not at all. What you've done is you've taken the same amount of energy and concentrated it directly, and when it hits at an angle, I've spread out that same amount of energy over a large area. It is less bright in any one spot. Because of the curvature of the earth, the rays of the sun at the equator are directly on. It gets heated much, much more quickly because it's more intense. Where we live, it is spread out, so we don't get as much of the intensity as we would at the equator. So places on the earth are heated at different rates. Not only that, land heats fast, water heats slowly. So if I hit water or I hit land, there's differences. Now, land cools off fast and water cools off slowly. And so one can give off heat longer The other one very quickly up and down. So where you hit, where it's on the Earth, if it's curved, all of these mean that it gets heated differently. That means the airs are different temperatures. That means it tries to mix up and it creates more weather. Okay? The energy that is given from the sun, 80% of it is moved around the Earth inside the atmosphere in the form of weather. The rest of it, about 20%, is moved around in ocean currents. And so the movement of all of that heat that is coming from the sun creates all of our weather. Why in the world do we have seasons? Okay, here's the deal. If the Earth were straight up and down as we were twisting, then we would absolutely have no summer, fall, winter, or spring. It would be the same temperature all year long. But because our Earth is tilted a little bit, okay, for here in June, up here in the northern hemisphere where we live, mainly is facing the sun. I get a lot of sun that is facing us, okay? We get hotter. In December, we're at an angle to the sun. We get less sun, and we get cooler. In spring and fall, we're a little bit more direct. The tilt is affecting us less, and so we're between the two extremes, and fall and spring feel about the same. And so this tilt tilts us towards or away from the sun at different times of the year. And it's totally opposite if you live in the southern hemisphere. I used to work with language and literature, and we would fly down to Santiago, Chile in summer, and people would spend 4 weeks studying 2 years of Spanish. Was it 2 years? Yeah, they could get, 4 weeks and a full year of Spanish, and then we spent a week going around the country. But the problem is we left in the middle of summer, right? But we go over the equator and we land in the middle of winter. I tell people that, and they pack. And there were several times in which people would land and go, oh, I have to go buy clothes, because they brought shorts and all kinds of short sleeve shirts, and it is winter. They had to go buy a coat and pants and sweaters and everything, because they didn't know after I told them. And so the tilt causes the seasons. Now here's the deal. If the tilt were further, okay, more tilt, that means the winters would be colder and the summers would be hotter, more extreme. If I had less tilt, I would have less of a season. So if we were straight up and down, that would be cool. Because whatever temperature you wanted to live at, you could find. Hot would be the equator. Moved a little bit north or south, you get a little bit cooler, a little bit cooler, a little bit cooler, and it would be that temperature all year round, the same temperature. You could find your temperature and be there. We don't have that, but many people do enjoy the changes of the season. Seasons. The reason we have a season, all right, in that the climate or the weather is different in winters and summers, is because of the tilt of the rotation of the Earth. And so our tilt is about 23.5 degrees from straight up top. So it would be 0 if it was straight up and down, but it's tilted to the side. That allows one hemisphere to be pointed more towards the sun at one point in the year, and the other hemisphere to be pointed towards the sun in the other. And so for us, summer is in June in this particular figure. In Australia, the summer is in December. So I've got a feel for all of those people who dress up as Santa in Australia, because that is the wrong time for the outfit that Santa Claus wears. But it is because of the fact of that tilt. Now that tilt is the same orientation as it goes all the way around the sun. This is why one side changes and the other side changes. In terms of winter, up in the northern hemisphere we get much less of the sun, and so overall we have cooler temperatures.